Okay, good afternoon, everybody. It's time for us to get started. So I thought just before we get started, I'd give you a reminder that we do have a test coming Friday. Because of the strike and the impact on the semester, the test is now going to be a little different. It's a 50-minute test in a 50-minute period, so people who are getting accommodations from the Blumman Center hopefully have those time accommodations in place already. I finished writing up sort of an official information sheet this morning. I didn't get a chance to get it posted, so I'll get that up this afternoon. It's going to be based on lectures 8 through 14 inclusive, so anything we did on those lectures could be there. You already sort of have a sense for what the tests are going to be like. I might recommend that you just practice working as quickly as you can. I've got the test more or less finalized. It's got 4 questions. I wrote up the solutions this morning. It took me about 13 minutes to write up the full solutions. So your writing time should be about 13 minutes. The remaining 37 minutes are sort of time to think, time to try stuff out, time to get it wrong and restart. So I think the test is a good length of time. Make sure in the test you're kind of explaining where things are coming from, you're showing equations and symbols, and then you're putting your numbers in. All of those details count. If you're looking for perfect marks on a question, your answers should look like the things I do in class, so it should reflect that level of detail and explanation. Like I mentioned last day, if you wish, you are allowed to bring in a sheet of notes to the test, 8.5 by 11, handwritten, single-sided, please. No limits to what you can put on that sheet. Anything you want is fair game. So anything you can think of that might be applicable, you are allowed to write on that sheet. I will not be policing it. The problem session is going ahead this week. That's probably good study for you. So there's some good practice problems in there. You can have all the help you want. I did post the problem session 1 grades this morning, and I've got those papers ready to give back to you. Dylan marked them, so they're ready to give back with some feedback. You may notice that the mark you get on the paper is not the same as what's posted in Brightspace. That's because you kind of have 2 portions for the mark for a problem session. You get 50% for showing up and doing some work. The other 50% of the grade comes from your score on what you passed in. So you kind of already automatically get a base 50% just for showing up, and then the work that you pass in and get your answers for, that kind of brings you up. So everybody did pretty well on that. I think that's everything I wanted to mention. Does anybody have any questions? We'll write our test in here, so same time, same place. So last day we did Kirchhoff's laws. We talked about ammeters and voltmeters. So we got finished with our resistor circuits, and today we're going to start RC circuits. They're still DC circuits because the current does flow in one direction. And I know you've been covering RC circuits and things like that in the lab. We'll kind of slow down at this point because I'm not sure how much detail you would have done in Physics 1051. And we'll just try and take our time a little bit going through the theory of this stuff. So to recap what we've done so far with capacitors and resistors, we looked at capacitor circuits. We know that we connect capacitors to a battery. When we do that, charge flows until we get the maximum charge stored on the plates. It stores energy. We can have parallel combinations or series combinations, or we can have a combination of both. And we know that the charge will flow until it's fully charged up, at which point charge will stop flowing. So what a capacitor circuit does is it allows charge to flow for a certain amount of time. Charge flows until it gets charged up. So that's what a capacitor circuit does. With our resistor circuits, we also had series and parallel and combination circuits. We know with resistor circuits, when we connect to a battery, it will draw current, and current will flow through the circuit. It's not time dependent, so the current will flow until we disconnect the circuit. But the resistors that we put in the circuit will impact the current. So a resistor circuit sort of defines how much current we can draw. A capacitor circuit defines how long the current will flow. So putting them together gives us things that we use in timekeeping circuits, like your intermittent wipers. That's how they know to come on and turn back off. It's because there's RC circuits in the circuitry of those. Another place you see RC circuits would be in the AED machines. They're kind of posted on the walls everywhere. They have a large amount of charge stored in capacitors. When you put them on somebody's chest, that makes a circuit with the body, and you hit the button, it makes a circuit, and it delivers charge through the circuit and to the body. So that's some places where you can see RC circuits. So there's a sentence that I kind of hope is the main takeaway from all that stuff. Our resistance essentially controls the size of the current, and the capacitor turns it off and on. We're going to look at two circuits and the nature of those circuits and how they work. We'll look at a circuit where a capacitor gets charged up. So we take a capacitor and a resistor, we connect it to a battery, and we turn it on. In these circuits, we start with the switch open, so there's nothing happening at the beginning. Then we close the switch, charge flows off the battery through the resistor into the capacitor. It's going to flow freely. Charge will start to build up on the capacitor. It will get harder and harder to put more charge on the capacitor. Eventually it will be full and the current will stop flowing. So that's what a charging circuit is going to look like. We know that current, charge, and potential, those things are all going to change over time. Our discharging circuit, we start with a charged capacitor, we connect it to a resistor. When we close the switch, these charges will be repelled, so they'll start to flow around the circuit. They'll just keep going until it's completely discharged. Once it's discharged, the current will turn off, and again, current, charge, and potential all change over time. So we're going to look at both of those circuits. Our goal, what we're going to start with, is we'll look at both circuits. We're going to use Kirchhoff's law to find a description of the charge as a function of time, and we'll use that description to tell us about current and potentials. So that's where we're going with this. We're going to start with the discharging circuit, just because it's a little easier to do mathematically. So here's our picture again. So I've written out all the initial conditions rather than making you write it down by hand. So what's happening at the beginning, before we get started, is we have a capacitor and it's completely charged up. The way we got it charged up was a little while ago we hooked it up to a battery. So that's how we get it charged. It has a maximum amount of charge, which tells us that it has a maximum amount of potential across the plates. If our switch is open, the current cannot flow at all. That tells us that the potential across the resistor at the very beginning has to be 0. Okay, so this is where we're starting from. And the current can't flow because the switch is open. So our next step will be to close the switch and talk about what happens. So just to keep everything all together on the one slide, if you need a reminder, this is just a smaller typed version of the previous slide. At t equals 0, we're going to close the switch. So that means we're going to take this down, we're going to close the switch, and now that's a solid line across. If we have the solid line across, the charge is allowed to flow and it will start to move. We have a bunch of these positive charges here. They're repelled by each other, you know, like forces repel. Because they repel, they start to leave. Because the charge is flowing around the circuit, that's what we've defined as current. So this current is flowing around our circuit. Okay, we're good with the setup? So this is what happens as soon as we close the switch. The charge starts to move, moving charge is current. So we're going to talk about what's happening at some time after 0 and before it's completely discharged. Okay, so what's happening in the discharging process? So where is it? Somewhere in the middle. So at some generic time t, the capacitor will have some generic charge that we can call Q. So it will have an amount of charge Q on the plate. And if it has a charge and a capacitance, it's going to have a potential. The potential I'm going to call delta V, and I'll put a C on it to say delta V across the capacitor. And we know that potential difference across the plates of a capacitor is the amount of charge on the plate that we defined as Q divided by the capacitance C. So that's what's happening with our capacitor at some amount of time after we've closed the switch. We can also ask what's going on with the resistor. It's going to be a potential difference across the resistor. So for our resistor, I put in a minus sign right here for the potential difference. For our capacitor, when we come around, as we come around, we go from a negative charge to a positive. That's an increase in potential going across the capacitor. So that's an increase. As we come from the resistor, it goes from a high potential to a low potential. That's a decrease or a drop. So you've got to be careful with the potentials here. When we talked about Kirchhoff's laws, we recognize that potential can increase or decrease. For our capacitor, it increases, and our resistor, it decreases. So now our next step is we'll write Kirchhoff's potential law, or the loop rule. So let's draw a loop. Come around my loop this way. And our loop rule says that the potential difference across the capacitor plus the potential difference across the resistor, because it's a closed loop, has to be equal to 0. So Kirchhoff's potential law is true, even if it's not just a resistor circuit. It's true in any circuit. Let's put in what we know for the potential of the capacitor, Q over C. And then for our resistor, it's minus I times R equals 0. So Q over C minus I times R equals 0. So now our task is to try and solve this to tell us the charge as a function of time. This equation looks a little bit difficult to solve. C is a constant, R is a constant. Q and I are not truly independent, right? So we get current because charge moves. So we come back to our definition of current. In general, when we did our definition, we said that our current was the amount of charge that moved over an amount of time t. So it's the change in charge over the change in time through some area. So that's our general case. For this specific case, we get the flow of current happens when we decrease the charge on the capacitor. When this Q gets smaller by an amount, that's when we get the current flow. Hopefully that makes sense. So dQ has to be a decrease. That means our current I is negative the amount of charge that flowed off the plate, dQ, divided by time. So current flows when Q decreases. Okay, that's the last little bit we need to pull this together. So now what we're going to do is we're going to put this in for our current, and we're going to solve this equation. So you may have solved this in Physics 1051. You might have skimmed over the solution. You might have not seen it at all. We will definitely go through it in this class. So any questions to hear? All right, so now we'll say we wish to solve this. So Q over C minus I times R equals 0. Q over C minus dQ by dt times R equals 0. Minus times a minus gives us a positive. I'd like to have dQ by dt by itself, so I'm going to divide both sides by the resistance R. q over rc plus dq by dt equals 0. Now I want dq by dt on the left by itself. I'm going to bring the q over rc to the other side. I'd like to have this q over here on this side, so I'm going to divide both sides by q. This is getting something closer to what I'd like to solve. I'm going to bring my dt up to the other side. 1 over q dq equals minus 1 over rc dt. I think if your math prof heard me say that, he or she probably wouldn't like it. I'm just bringing my dt up here. That's what you do in practice. In math class, they have like a lot of different ways to describe it. So if you care about that little nitty-gritty detail, you're probably going to pick that up in your math class. So I've got 1 over q dq is minus 1 over rc dt. If I want to find q, I'm going to have to integrate both sides. So I'm going to integrate 1 over q dq, integrate minus 1 over rc dt. R and c are constants. They can come outside of my integral. Okay, so these integrals are definitely doable. So let's put on the limits of the integral first. So for my limits of my integral, I'm going to start at t equals 0. And I know at t equals 0, the charge is the maximum charge, which I call q0. Okay, so that was one of our initial conditions. At t equals 0, the charge was the maximum. So my initial time is 0. My initial charge is q0. We're going to integrate to a generic time t, where the charge is that generic value q. So those are going to be our final spots. The integral of 1 over q dq, that's the natural log of q, evaluated at q and q0. That's going to be equal to 1 minus 1 over rc. The integral of dt is just t, evaluated at t and 0. For the limits of our integral here, putting in the limits, natural log of q, evaluated at q and q0, is natural log of q, subtract natural log of q0. When you subtract two logs, that's the same as taking the log of the arguments divided. Q over q0. And then for our t evaluated at t and 0 is t minus 0, or just t. So I can put those bits in. Got the natural log of q divided by q0 equals minus t over rc. Okay, this is not bad. We could stop here. We don't, because we'd like to have an equation that says q equals, which means we need to get rid of the natural log. So that means we have to do e to both sides. So both of those are going to be exponents of the natural number e. So e to the natural log of q over q0 is just q over q0 equals e to the minus t over rc. Okay, so you raise both to the e. Then I'm just going to multiply my q0 to the other side to get my charge q as a function of time t is q0 e to the minus t divided by r times c. This r times c, this is going to keep popping up. This is special, so we're going to make a new definition. That definition is the Greek letter tau, and that's going to be r times c. That tau is called time constant. The units of tau are kind of important. So tau is resistance times capacitance. So the units of tau will be units of resistance, the ohms, times the units of capacitance, which are farads. An ohm is a volt divided by an amp. A farad is a coulomb divided by a volt. So that leaves us coulombs over amps. And we hopefully remember that an amp is a coulomb over a second, leaves us with seconds. Okay. So the units of the time constant are time, so that's a good thing, because we can't have units up here. So let's write that down one more time. So our charge, as a function of time, is our maximum value Q0, e to the minus t over tau. It tells us that our charge goes through an exponential decay over time. So it starts big, and over time it goes to 0. So this is the charge on the capacitor plates as a function of time for the discharging capacitor. Okay, so charge is a function of time on the plates for discharging capacitor. The two behaviors we'll just mention before we look at a graph. If our time t equals 0, this whole thing is 1, and q equals q0. So that matches our initial conditions. If our time gets really big, then this value here goes towards 0, and it gives our charge to be 0, which matches the description. We have a discharging capacitor, so eventually q goes to 0. So that behavior matches what we know is what's happening. Okay, any questions before we move on? And I think that's probably the sort of equation you solved in a math class before. This would be fair game for a test. I could ask you to do this as a test problem, derive the equation for charge as a function of time on a discharging capacitor, and that's what I'd be looking for. So let's do a graph of that charge as a function of time. I cheated a little bit because I didn't want to write out a whole bunch of boring numbers in class, and I didn't want my graph to look bad. So I kind of got it set up on Excel for myself. So here's my equation for my discharging capacitor. That's what we just cooked up. I copied out my diagram again, so we have that handy. And what I'd like to plot is my charge Q as a function of time t. For my time t, on my axis, I'm going to plot it. I'll start at t equals 0. My next time I'll plot it will be at 1 time constant. Then my next time will be 2 time constants, 3 tau, 4 tau, 5 tau, and so on. So I'm going to plot it in multiples of the time constants instead of plotting it in seconds or minutes or microseconds or whatever. So multiples of the time constant. So my data table here, let's just look at the first column. So my first column is my time. That's what's going on my horizontal axis. I want to go t equals 0, tau, 2 tau, 3 tau, 4 tau, 5 tau, and so on. So the next thing I'd like to figure out is what is t divided by tau? Well, 0, 1, 2, 3, 4, 5. Okay, so that's the next column here in my data table. And then the next thing I'd like to figure out is what is e to the minus t over tau. That's a number you can just use your calculator or spreadsheet to figure out. And that's what those numbers turn out to be. So my Q value is going to be Q0 times each of these numbers. So that's what that table is. So let's fill in some of those values. At t equals 0, my charge Q is Q0 times 1 for Q0. It's the first point on my graph. So that's my maximum charge. That's the biggest it's ever going to be. That's right at the beginning because that's when it starts to discharge. 1 time constant later, my charge is now going to be Q0 times 0.368, round off a little bit. Okay, so my charge goes down to about 37% of the original charge after 1 time constant. So my next point is down here. After another time constant, Q is equal to Q0 times 0.135. We're down to 13.5%. Then next, Q equals Q0 times 0.0450. So we're down to 5% after 3 time constants. After 4 time constants, Q is Q0 times 0.018, about 2%. Q equals Q0 after 5 time time constant 0.007 less than 1%. This 5 tau, when we get down to our original charge being less than 1% of the original charge, here's where we say, at this point it's discharged, this is good enough for us. So it takes 5 time constants to become approximately discharged. If you kept going with your table, and you certainly could because it's easy to populate an Excel spreadsheet, what you would find is this charge never really honestly and truly goes to 0. Okay, that's kind of interesting because this function, e to the minus t over tau, that never gets to 0 until t gets to infinity. So q never really gets to 0. However, it does get pretty close, and q is approximately 0 at t equals 5 tau, and we say it's discharged at this point. Let's see. So if I ask a question on a test, how long does it take to discharge this capacitor? I'm not looking for the smart aleck answer of it will never discharge. I'm looking for a time of 5 tau. That said, I tend to be a little pedantic sometimes, so I'll probably ask the question, how long does it take to become approximately discharged? So those two things mean the same thing, and you're trying to find time equals 5 tau. So if you connect the dots, you get a graph that looks like this. And it goes so close to 0 that I can't really make a difference in my pen mark. And then the last thing I might say is that when our capacitor is fully discharged, as Q gets to approximately 0, that means there's no charge left on it, which means charge is not flowing anymore. That means current goes to 0. So when it's discharged, the current goes to 0. That means that if we're looking at circuits, after a capacitor discharges, it acts like an open circuit. Current doesn't flow anymore. So a fully discharged capacitor looks like an open circuit. That'll be a tool that we'll use in some circuit analysis. Okay, so there's our charge, the short and long-term behavior. Any questions here? Okay, let's get our expressions for current and potential next. And then we could do a couple of examples. So there's our equation rewritten so we don't forget. Find expressions as a function of time for current, potential on the capacitor, and potential on the resistor. So for our current, we're going to start with what we said, that we get current flow when the amount of charge on the capacitor decreases by a little bit minus dq. So there's our expression for current as a function of charge. That means we're doing negative of the derivative of this function right here. So minus d by dt qo e to the minus t over tau. Let me take my qo outside first. When we do derivatives of e functions, they're special. So a derivative of an e function is, first of all, you get the e function itself, e to the minus t over tau. Then you have to multiply by the derivative of the exponent. And this bit will be minus 1 over tau equals minus 1 over r. Is that something you've seen in a math class before? Derivatives of those e functions? I don't remember in what math class I did that. So, yeah, so that's something I sort of expect you to be able to do. So let's fill this bit in. I've got minus qo e to the minus t over tau times minus 1 over rc. Minus times a minus is a plus. I'm going to bring my rc to the front. I could leave it here, but I'm not very satisfied with this part. When I see qo over c, that's my maximum charge, my maximum initial charge, divided by the capacitance. That's the maximum initial potential. So this bit is my delta V0. Okay, so that was the initial potential difference across the capacitor. So my next step is I've got delta V0 divided by the resistance, e to the minus t over tau. This bit, delta V0 over the resistance R, my maximum potential difference divided by my resistance, that gives me my maximum current. So that's initial potential difference across the resistor divided by the resistance. Gives me my initial maximum current, I0. So we can write down our final expression. Our current through that circuit as a function of time is the initial current, which is a maximum, times e to the minus t over tau. So there's our current as a function of time. It starts at a maximum value and it goes to approximately 0 after 5 time constants. So that's the current done. Next we'll do the potential across the capacitor. Potential across the capacitor, we decided to call that Vc. So potential across the capacitor is the charge divided by the capacitance. Our charge is given by our charge equation, QO e to the minus t over tau, divided by our capacitance C. QO over C, that was our initial maximum potential. So our potential difference across the capacitor is the maximum potential times e to the minus t over tau. Same behavior, it starts with an initial maximum potential, falls off exponentially, goes to about 0 after about 5 time constants. So that's this one. Last, we want to find the potential difference across the resistor. We can use our Ohm's law here. Delta V across the resistor is the current through the resistor times the resistance. Our current was I0 e to the minus t over tau times the resistance. So I0 times R e to the minus t over tau. IO times R, that's our initial maximum potential. So delta V across the resistor is delta V0 e to the minus t over tau. So we notice that these potentials start at the maximum value, they decrease over time, and we notice that they're equal, right? So the potential across the capacitor and the resistor is equal, and that makes sense when we look at the picture, right? So there are two things connected in a circuit. Kirchhoff's law says we have to have the same size of potential across both of them. So this one supplies the potential, and we get a drop across the resistor, and they have to have the same magnitude at all times. Okay, questions? Okay, so there's our I's and our delta V's. Now let's work on some examples. So, for this example, there's a lot on this slide, but I promise this little box of empty space is enough to solve it. So we've got an RC circuit. The diagram shows that the capacitance is 6 microfarads, the resistance is 2 ohms. So there's an RC circuit. We're going to close the switch at t equals 0, and we're going to allow it to discharge. So that's what's happening here. And we've hooked up this circuit to an ammeter, and we've plotted the current as a function of time for our circuit. So that's what this graph is showing. The two things we're asked to find are what are the time constant and what's the initial charge on the capacitor from the data that we're given. So for our time constant, here's where we remember that our time constant tau is the resistance times the capacitance, 2 ohms times 6 microfarads, equals 12 times 10 to the minus 6 seconds. These times are really small, so sometimes we would write that as 12 microseconds. So you might see it with the exponent or with one of those prefixes. So call that part A. The second part, what is the initial charge? So let's think about what we know. And it doesn't look like we know lots to get started. We know the resistance and the capacitance, and we also know the initial maximum current. So our initial maximum current, I0, is equal to 5 amps. We can see that on the diagram, and we can confirm it with the data table. At this point, we might remember that the initial potential difference across the capacitor or the resistor, they have to have the same value, would be I0 times the resistance R. That means we can find that initial potential difference, delta V. The delta V0 is going to be the initial current, 5 amps, times the resistance, 2 ohms, equals 10 volts. So there's the initial potential difference across the resistor. That has to be equal to the initial potential difference across the capacitor. So delta V0 is also the charge on the capacitor, Q0, divided by C. And I'm putting all these zeros in there because we're talking about what's going on at time t equals 0, all of the initial conditions. That tells me that my charge QO is delta VO times the capacitance, 10 volts, times 6 microfarads. Gives me 60 times 10 to the minus 6 coulombs, or 60 microcoulombs. Okay, any questions? What else? A part C wouldn't be very challenging, but you could ask how long does it take to discharge? You would take this time constant, multiply it by 5. Something you could do. And I guess you could ask for values of I, Q, or potentials at different times. So you just plug those times into the equations and find it. Okay, so we'll move on from that one. So this one has a lot more words. The switch in the figure has been in position A for a long time, and it's changed to position B at t equals 0 seconds. So we're starting over here and then switching over here. And then we'd like to know some things about charge and current and how long it takes to discharge. So before we get into the specific questions, let's just make sure we understand what's happening in the circuit and how we can look at it at the different points. So for t less than 0, that means the switch is in position A, and this branch is not connected at all. If this branch is not connected, there can't be any current flowing through it. So for t less than 0, we've got our switch in contact at point A. We've got our 9-volt battery in contact with a 4 microfarad capacitor. What happens here, it's in position for what we say is a long time. It means that the capacitor gets fully charged. It's got a potential across the plates of 9 volts. So this is what's happening at the beginning. V across the capacitor is V0 equals 9 volts. If we cared, we could calculate that the charge across the capacitor is C times V0, 9 volts times 4 microfarads to get 36 microcoulombs. Okay, so we could do that at the beginning if we're just trying to think about how this sets up. Then at t equals 0, we flip the switch. So then the new circuit has got this 9-volt battery, the 4 microfarad capacitor, and the switch is now flipped over to position B, where it's connected to a 25 ohm resistor. In this picture, our battery is not connected at all. That means no current flows out of the battery into this circuit. So if we wish, we can redraw it to leave off the battery altogether. If this were a test problem and you drew this picture and you didn't draw this one, this is still correct. I'm redrawing it just to give us a clear picture of what's happening here. So this is kind of just to help you visualize it. But this is certainly not incorrect. This is true. It's actually what's happening. We've just moved that switch over. So at t equals 0, we flip the switch. What happens the moment that we flip the switch is that the potential across the capacitor is the same as the potential across the resistor, which is that initial maximum potential of 9 volts. So as soon as we flip the switch, the capacitor and the resistor both have a potential difference of 9 volts. The charge on the capacitor, just as we flip the switch, is still the maximum charge because it's just about to flow. So this is how we get started with this problem. The current as it starts to flow is going to be the maximum current. Any questions? And then all of those things are going to decay over time exponentially. So now let's get into what the questions are even asking. So what is the charge on the capacitor immediately after the switch is moved? So we've got all that work done already. Q equals Q of 0 equals Q0 equals 36 microcoulombs. So that's the charge on the capacitor. What is the current through the resistor right after we move the switch? So we'll use Ohm's law, V equals IR. So the current is going to be the potential, V0, divided by the resistance. So we're talking immediately after the switch, we've got our maximum current, our maximum potential. 9 volts divided by 25 ohms equals 0.360 amps. So that's the current right at time t equals 0. Then it asks, what's the charge and the current some amount of time later? So we'll use our charge and current equations to find those. So C, Q of t is Q0 e to the minus t over tau. We could find our tau here off on the side. So our time constant tau is R times C, 25 ohms times 4 microfarads to give us 100 microseconds. So there's our time constant tau. So we've got 36 microcoulombs times e to the minus 50 microseconds divided by 100 microseconds. All that through the calculator, we should get 21.8 microcoulombs. So there's the charge on the capacitor at 50 microseconds. So a half of a time constant, basically. And then part D is what is the current. Similar sort of equation, I0 e to the minus t over tau. I0 was 0.360 amps, e to the minus 50 microseconds over 100 microseconds. Gives us a current of 0.218 microfarad. So there's the current through the resistor, through the circuit at 50 microseconds. And then our last little bit, how long does it take for the capacitor to discharge? So that time t is about 5 time constants, 5 times 100 microseconds, 500 microseconds, or 5 times 10 to the minus 4 seconds. Okay, any questions? I didn't have another example I wanted to do. I was hoping we would get time to start on the charging capacitor. But we've only got 5 minutes. I think it would be not very pleasant to kind of start it and stop a couple of minutes in. So if everybody's okay, we'll quit here for today. And we'll start the discharging capacitor on Wednesday.